Welcome, everybody. This is Hasta La Vesta, which is the Dawn mission's celebration of our mission's departure from Vesta. We spent the last 14 months exploring this very planet-like asteroid world and using a variety of instruments and techniques in order to better understand the early history of our solar system. Today, we're going to be talking with some of the engineers and the scientists from the Dawn mission about their experience both helping to drive the spacecraft, helping to operate instruments, also about the exciting results that are coming from the spacecraft today and the science that's probably upcoming as we begin the analysis phase on our cruise away from Vesta and on to Ceres. Something else that we're really excited to bring to you today is the launch of the Asteroid Mappers web interface. Asteroid Mappers is a chance for the public to get involved in analyzing the data, much like the science team does every day. So in partnership with CosmoQuest, the Dawn mission's education and public outreach team has been working to provide an online interface where people can have the chance to mark craters, to look for boulders, to go searching for tectonic features across Vesta's surface, in a way to help the science team understand more things about Vesta, and even more importantly, to give the public a chance to participate in really what it is to do science with a NASA mission. So we're really, really excited to share that. And actually, that's how we'd like to kick off today. So we've also got here Pamela Gay. Pamela is the lead for the CosmoQuest Enterprise. And they are the folks who have been putting together asteroid mappers for the last several months. Actually, we've all been working together for the last year or so, actually, to try to bring this to the public. So the website went live about 30 minutes ago. So Pamela, welcome. Thanks for coming.
Well, thank you. I'm actually coming to you from the Scope Out event at Cincinnati Observatory. So if my video is a little bit laggy, I apologize. I promise to hand you over to people with better internet in a moment. The Asteroid Mappers project is something we're extraordinarily excited about because the images that are in this project are images that aren't fully released to the public yet, in the sense that you can just go and happily download all of them from the planetary data system. These are images that you may be one of the first people to get to go out and look at them and explore them. And you're going to be helping the Dawn team basically trying to find how is this little rock that's not even round in the asteroid belt both very much like a planet and very much unlike a planet. And I think all of us, both at Dawn and at CosmoQuest, have been looking at these images and had a moment of, how did that happen, where we're picking up our computers and rotating them, because the surface is so lumpy that you end up with craters on various sides of hills, and you can see the shadows splaying out as the topography changes, and it's just very beautiful imagery, and it's kind of like what would happen if Dr. Seuss designed the planet is the best way I could think to describe it.
Yeah, I think that that's a really good point. One of the things I've been asked is, well, we've already got moon mappers, so why do we need asteroid mappers? We already know how to count craters. Well, it turns out that Vesta's a lot different from the moon. It's very similar, actually. It reminds us in many ways of the moon. It is actually, for an asteroid, incredibly round. It's huge. It's actually about the size of the state of Arizona, and it's got these features that are reminiscent of our own moon. But one of the interesting things about it is that because it's had a different impact history, it lives in a different cosmic neighborhood. It's been embedded in the asteroid belt for its entire existence. And so it's telling us another piece of the history of the asteroid belt. So it's kind of exciting from the perspective of getting more eyes on the images, because it takes our one case example. We understand the moon pretty well, we understand the cratering history of the moon pretty well, and we need more and more examples of this so we really understand what the earliest phase of the solar system was. And since Vesta was one of the first things actually to form in the solar system, we have this new picture of kind of what the earliest phases look like. And you mentioned that Vesta's surface is all kind of lumpy and different looking from the moon. It turns out that Vesta's gone through an incredibly interesting history. It formed, it differentiated, it's very much like a planet in that sense, but probably as it's been changing its environment and been beaten up by these different impact events, it's actually created impact tectonics like we've never seen on a planet before. Really amazing features that are unique to Vesta, landslides, all kinds of mass wasting, huge impact ejecta blankets, and places where the material is falling down the sides of craters and sweeping into crevasses. Just an amazing place. So definitely something different out there compared to even just the Moon Mappers project. So we're really, really excited about that.
So I guess the last thing I'd like to say is, if you've looked at the moon, you haven't looked at Vesta. This is a world that's covered in wrinkle ridges, that is covered in these neat troughs, that has scattered boulders at the bottoms of craters. And we'd encourage you to come join CosmoQuest and help us be part of exploring our solar system and become a part of doing NASA science. And I'm going to disappear and introduce a bunch of real-world people to doing science here in Cincinnati, and I look forward to getting to know all of you out online. So thank you so much, and Brittany, good luck on this entire broadcast.
Thanks very much. Pamela's been a real key part of this development, actually, for the last few months, so we're really excited to have her and CosmoQuest on board. So what we thought we'd do is go ahead and go on to our engineering team. One of the things that's really exciting that makes this mission so different from others, and in fact, the way it's flown, it has a different engineering background. It's a different spacecraft. It's got huge solar panels that power the instruments, but it turns out that it's the engine for the spacecraft that really makes a lot of the science possible for Dawn. It's a unique spacecraft in the fact that it'll be the first one. In fact, just 3 days ago, was the first spacecraft to ever leave orbit around one target body and go on and head for another. So it's a real human first in terms of spaceflight. And so we've got two of the engineers here. We have Chuck Garner and we have Tim Weise. Chuck was the ion engine lead, and Tim is the spacecraft team lead. And so I thought we'd talk to them a little bit about what it's like to be an engineer for the Dawn team and to fly the spacecraft every day. So I thought maybe actually let's start with Tim. Tim, you want to wave and say hi to everyone? So Tim is joining us from JPL. Tim, why don't you tell us a little bit about your background?
Let's see, I've been on the project since about 2004. With the early development of all of our operations processes. Before that, I worked on the Spitzer Space Telescope at JPL, and prior to that, I was at Hughes Space and Communications working on geosynchronous comm satellites.
So since we've been talking about Dawn and its departure from Vesta, I know that you're the spacecraft team lead. Is that correct?
Yes, it is.
So what does that actually mean? What does that mean to somebody who's not on the engineering team?
Okay, so my team's primary responsibility is to operate the spacecraft, make sure that it's safe, all the operations are safe. We build all of the sequences of commands that are used to tell the spacecraft what to do every minute of the day. So we've been in flight for almost 5 years now, and every minute of that time has been planned by the engineering team, and then while at Vesta we had the science team supplying the science inputs. So we have to make sure all of that's safe, and then we also have to look at all of the telemetry that comes down to make sure that the spacecraft is operating nominally and respond to any glitches or hiccups, any signs of something going in the wrong direction, and then planning responses to correct any problems.
So would we call you the Captain Kirk of the engineering team?
Almost, maybe first officer.
Okay. So you mentioned telemetry. That's kind of our way of talking back and forth with the spacecraft, right? It's basically the electronic signals that the spacecraft is radioing back to us through the Deep Space Network. Is that correct?
That's correct. Basically, every temperature, engineering parameters, whether a heater is turned on or turned off, what the current attitude is, where the spacecraft's pointed, all of that's recorded on the spacecraft, and then periodically we turn the high gain antenna towards Earth and downlink all of that data so that we can review it and make sure the spacecraft was operating nominally and achieved all of its objectives.
Okay, so tell me a little bit about how we got to Vesta, because I know you don't really just take a straight track. We do gravity assists and do a lot of manipulation. I think you have an image to share with everyone about that, actually.
Yes.
So we'll try to get that image up there.
Can you tell me which one it is?
Yep, it is off of the presentation that let me just double check here. So actually, Tim, why don't you describe to us while we get your image up what the trajectory looks like, why it is that we don't just fly straight to Vesta.
Okay, so basically what happened at launch was the launch vehicle put us on a trajectory that started us on our way towards Vesta. But we actually targeted a rendezvous with Mars to get a gravity assist. So between the time after the first 3 months after launch, we did a lot of activities to check out the spacecraft, making sure all of the components worked as designed. And then as the trajectory progressed, we designed month-long sequences that would tell the spacecraft to fire the ion engine in a particular direction so that we could fly by Mars at an altitude of 500 kilometers. And that gave us a gravity assist to assist us on our way to Vesta. And then beyond Mars, we continued with the same maneuver designs all the way into Vesta.
So basically, you're kind of stealing a little bit of energy from Mars, right? As you swing by, you use Mars to kind of push yourself a little bit faster.
Yes. Yeah, we got going a lot faster, and Mars got going a very, very, very little bit slower.
All right. So how exactly does that type of a maneuver work in terms of the spacecraft? What do you, I mean, is it just the direction, or are all engines burning at once? Because Dawn has 3, is that correct?
That's correct. We have 3 ion engines. We can only fire one of them at a time because of the design and the power requirements. But the interesting thing about flying by Mars was that we didn't use the ion engines at all from about 2 to 3 months before flying by Mars. The navigators designed a perfect trajectory so that we would just ease on past the planet, and so they designed it so that our trajectory would take us right within 500 kilometers of the surface, and we didn't have to do any maneuvers at all. It just kind of went by. As we got closer to Mars, we accelerated, and then it changed our trajectory in order to rendezvous with Vesta.
Okay, so right now we're looking at that. So we're kind of seeing the map of the trajectory that Dawn took. So we launched in 2007, you mentioned. So then if I'm correct, Dawn actually got going pretty fast compared to other spacecraft. Is that correct?
That's correct. We've gone around the sun several times in our trajectory, and you can see on this slide, it's a little bit hard to see, but the blue dashed part of our trajectory is all of the time that we were firing the ion engine. And so you can see as we approached Mars, it's a long orange bar before and after Mars. And so we didn't, the natural progression of the trajectory didn't require us to fire the ion engine during that time. And so we actually coasted for all of that time and did other engineering activities on the spacecraft, such as loading flight software and things like that.
So I have a question for you. What does it mean when a spacecraft safes? What is that really?
Okay, so most deep space spacecraft have what's called a safe mode. And basically the people designing the spacecraft, the developers, designers, analysts, figure out what the minimum set of equipment is required to maintain the spacecraft safety. And then it configures all of the equipment to be safe and puts the spacecraft in a sun safe attitude. So for us, we point our one side of the spacecraft, the plus X side, which is where the high gain antenna is. We point that at the sun and slowly rotate about 1 revolution per hour. And this state was heavily analyzed pre-launch to ensure that it would be safe no matter what happened on the spacecraft. With any kind of fault or anomaly, this mode would be safe. And so it's kind of the minimum set of things to keep the spacecraft alive.
Okay, so one of the things that I really remember from the mission. So actually, I was a graduate student at UCLA when this mission was starting out and launching, and so I went through launch, and I remember the approach. And I had actually moved on to a new position here in Texas, and I remember what it was like for me to see the very first pictures when we were on approach. And I know you wanted to share those, so I'm going to go ahead and share those as well. But can you tell me what it must have felt like as a member of the engineering team flying that spacecraft when this first few images of Dawn, or I'm sorry, of Vesta actually came up? What did that feel like?
That was truly amazing. I mean, we had been so focused on flying the spacecraft and making sure that all of the operations would be work correctly, make sure the science plan would execute correctly once we got to Vesta, and then to finally see the body resolve better than the Hubble Space Telescope images. You know, it was just a fuzzy blob. And then every week we got a new image as we got closer, and you could see more craters and more lumps and more grooves and all these very interesting science features. And it's just amazing to me.
Yeah, I totally agree. I remember just what it felt like. So I love this picture too because it shows what the best technology available at the time showed us of Vesta, the Hubble Space Telescope, this huge telescope out in space, and just to get those first, even the really fuzzy images, I just remember what an incredible experience that it was, and I'm sure that someone so responsible for the safety of the spacecraft must have just felt amazing. So I wanted to ask you one more thing, and that's if you were the spacecraft, give me like a day in the life of Dawn. What is it like? What's Dawn seeing now, right now? Or what's Dawn doing right now?
Right now, Dawn is firing its center ion engine, so that's the one that's in the middle of the bottom part of the spacecraft, in order to adjust our orbit and to rendezvous with Ceres. And so we started departure back in July, and we've been firing the ion engine as planned in order to change our orbit. So it seems pretty boring, because it's just sitting there firing the engine, but it has to do this all of the time. We expect to fire the engine 20,000 hours in order to get to Ceres, and that's about as much as we fired it to get to Vesta.
So basically, in spacecraft terms, Cassini or any of those big spacecraft are kind of like the big bulky sprinters, and Dawn's a little bit more like a marathon runner, or maybe the Iron Man competition, right?
Yes.
Working the whole time.
Yep, there's always something to do.
Well, that's really great. Okay, let's see. Let's actually get Chuck up and let's chat a little bit about those engines that make this whole thing possible. So everyone say hello to Charles Gardner.
Hello.
So Chuck is our lead ion engine engineer, and so he's been really a part of building the system that makes all of Dawn possible. One of the things that's really interesting is that Dawn is getting to do exploration of two different bodies, Ceres and Vesta, and they're pretty far apart, and it's got a very, very long mission lifetime. Generally speaking, so Dawn is what's called a Discovery class mission, which means it's one of NASA's lower cost missions. And so one of the challenges of doing low cost missions is figuring out how to get as much science as possible for the lowest cost. And one of the exciting things about that is that Dawn has actually been able to do all of this because of the ion engine. It's a relatively inexpensive and efficient way to do propulsion. And so it really is this ion engine that has made all this possible. So Chuck, why don't you tell us a little bit about the ion engine from your perspective?
Well, I started working on ion engines at JPL in 1981 when they were really just interesting laboratory instruments to work on. But by 1997, NASA had seen that ion engines could really help do missions cheaply, and they finally flew an ion engine on NASA's DS-1 mission in 1997. I started working on Dawn in 2001, and so here we are 11 years later, and it's really gratifying to see it all work out.
So tell us a little bit about Deep Space One. That was the first mission to really test these engines and prove that they were capable of deep space flight, correct?
Well, there had been other missions that flew ion engines as for testing them, but DS-1 was the first mission where it really drove the spacecraft to new places in the solar system.
Where did DS-1 go?
Well, it went to one comet, one asteroid. They were really flybys, so they're different from the Dawn mission, where Dawn has to go to that asteroid, which is a deep space asteroid. It's a big difference there because it's so far away, and go into orbit around that asteroid, do science, depart, and go to the next body. That's really a new thing.
Yeah, so really a new challenge completely. How did you get interested in ion technology? Any stories there, or are you a big sci-fi guy?
I went to school studying plasma physics, and I actually built a plasma device that was similar to the kind of ion engine design that NASA had come up with back in roughly 1980. And so I learned about this and learned about JPL, and so that's how I ended up at JPL.
So you ended up going from being just a physicist to being an engineer, building spacecraft. Right. What a fun transition.
Well, it's worked out great. You know, it's been great to see these engines developed in the laboratory as just interesting devices, and then actually see them actually used and actually be successful and get these spacecraft to where they've got to go. It's been great.
Okay. So what is an ion engine? What is it doing? What makes it different from? I think we've got a picture here of what the ion engine looks like. But what is it what makes it different from a standard hydrazine propellant engine?
Okay. Well, a standard hydrazine propellant engine, you have all of the energy stored in that chemical propellant. All you have to do is ignite it, burn it in some way. The gas gets hot. The molecules or atoms bounce around at very high speeds inside the thrust chamber of the rocket or the thruster, and then those gases are exhausted out. And the typical, you know, if you want to think about the best chemical propulsion engine there is, that was the shuttle main engine. And the atoms and molecules that exited that engine left at about 4,000 meters per second. With an ion engine, you don't burn the propellant. You actually accelerate the atoms out of the engine using electricity. And when you do that, you can get exhaust velocities nearing 30,000 meters per second. And so you get a whole lot more thrust for each pound of fuel that you carry on board that spacecraft.
And so I've seen this this example that basically the engine, when it's thrusting, has kind of the force of as of a piece of paper on your hand. Is that correct?
That's right.
So just about
20 millipounds or 90 millinewtons, something like that.
So really, really tiny, but all of that constant thrusting, like we just talked about with Tim, it just adds up over time, right?
It adds up. I did the math, and if I did the math right, you know, we've gotten over 7 kilometers per second. That's 7,000 meters per second of delta V. And we've gotten around 6 million Newton seconds of impulse from that little ion engine.
Yeah, just from these three little guys. So what do they look like on the spacecraft? Are they pointed all the same direction? Where are they located?
Well, there's one engine mounted in the center, like Tim Weise said. And then there's one engine on the outside of the spacecraft that's on the same side as the high gain antenna, and then there's another engine opposite to that, still on the outside. So there's call them two outboard engines and one center mounted thruster.
Okay.
That picture there, by the way, is a picture of the ion engine under testing. That's FT3, that's the center mounted engine, and it's exhausting its beam onto a probe so we could characterize the beam plasma from the engine to make sure that it was operating correctly.
Great. I think, and you had another couple images as well, right?
I think so.
So this is that engine where you're actually characterizing the engine, and then you had
characterizing the beam.
The beam. Okay, so that's the actual propulsion system.
Right. That's FT3, the center mounted engine.
Okay, great. I think I have another one that's this kind of dark gray image. Let me see if I can bring that one up. So what are we looking at here?
That is FT3, and that's just a picture of it mounted inside a vacuum chamber for what's called thermal vacuum system testing.
Okay.
And that engine is about a foot in diameter, and that's what's used to provide the propulsion for the Dawn spacecraft.
So as one of the engineers, did you actually get to bolt this on there?
Yes, I pretty much bolted it on. Yeah, that is correct.
How fun. So you actually got to see, got to wrap your baby up before sending it to the Cape, huh?
Of course, it's complicated. You don't just bolt it on. You also have electrical connections and propellant connections and things like gimbal connections and things like that.
It's kind of a long process, a lot of I's to dot and T's to cross, I imagine.
Right.
Well, thanks very much. I was wondering if we actually had any questions yet from. We had several questions actually emailed in, and I know we've got maybe a few questions out online if anyone wants to answer or wants to ask any of the engineering team. Let's see. Let's go ahead. Trying to find my questions. Well, in the meantime, if you guys will hang out, we'll go and talk a little bit about the science while we wait and get a few questions from the public listed, and then we'll come back to our engineering team. So thanks so much for joining us. Certainly very exciting. Oh wait, we did really quickly. We just got one about xenon. So what is the question?
Oh, it looks like it was asked on YouTube. Hi, this is Nicole. I'm the faceless voice. It says, is xenon the only operating fluid you can use, or is it just the best currently available?
Xenon is not the only gas that we can use, but it has a lot of properties that make it very, very desirable. It operates. It's used because the name of the game in space is to get as much thrust for each kilowatt of power that you have available, and power is greatly limited. You're limited by the size of the solar arrays, and so we can get pretty much more thrust for each pound of fuel using xenon than we can using something like neon or argon or krypton or something like that. It also stores at a very high density. The tank of xenon in the Dawn spacecraft would pretty much fit into the trunk of your car, and yet it's providing as much velocity change to the spacecraft as the 100-foot tall rocket that put Dawn into space. The density of the xenon in the Dawn tank was something like approaching twice the density of water. In other words, if you had a gallon jug of water that weighs about 8 pounds, if you have a gallon jug of xenon stored on the Dawn spacecraft, it weighed closer to something like 14 pounds.
That is pretty incredible. So saving you not only in terms of energy, but also in terms of mass you have to launch off, correct?
Right.
So actually, I think we've got a question that's maybe related. It's how much xenon does Dawn actually have on board? And how many, given how the engine is working right now, how many hours do we think it's going to totally have to burn?
Well, we've got about 162 kilograms of the original 425 kilograms of xenon that we put into that little tank that I bragged about that you could put into the trunk of your car. Mm-hmm. But right now we could operate that engine for around 30,000 hours.
Okay, wow, pretty long time.
And so that's more than enough to get us to Ceres and do the orbit operations at Ceres.
Great. So actually, and one more question, let's ask to Tim, actually. So Tim, can you tell us how fast Dawn is traveling right now in relation to Ceres, and how is that going to change over the next few months?
Well, what we're actually going to do between now and arrival at Ceres is we're right now basically matching the orbit of Vesta around the Sun. And then to get to Ceres, we have to match the orbit of Ceres around the Sun. And so the difference between the Dawn spacecraft velocity in Vesta right now is only about 100 miles per hour. We're slowly accelerating away from Vesta, and our relative velocity to Ceres is much higher. It is, well, I don't have it in front of me. It's on the order of 10,000 kilometers per second. And that's because Ceres takes 4.6 years to get around the sun, and Vesta takes 3.6 years to get around the sun. So their speed in space is very different. And we're going to change the velocity and slowly accelerate, or actually decelerate around the sun to slow down to match Ceres' orbit. And then as we get closer to Ceres, we'll kind of gradually approach, just like we did with Vesta.
So it's a little bit different there again from another spacecraft because you're doing that deceleration, right?
Yes, it's a very controlled, slow arrival. It's not like arriving at Mars where you're going really fast and then have to brake suddenly to slow down and do your mission.
Great. All right, well, I'd like to thank you guys. You're welcome to hang out and maybe answer questions at the end if you've got time, but let's go ahead and talk a little bit about science. For those of you who are maybe just joining, this is the Hasta La Vesta celebration of Dawn's departure from Vesta, and we've just spoken with our engineering team. We're going to move on and discuss a little bit about the science, and I thought to kick it off, let's go to Vishnu Reddy. Vishnu and I have been friends for a while now. Vishnu has actually had a long travel history, shall we say, to get to where he is. He's currently joining us from Berlin. One of the cool things about Dawn is that it's actually an international mission. The cameras were built in Germany. The spectrometer was built in Italy, and then the remainder of the spacecraft was actually built in the United States, including the gamma ray detector, which was built at the time, I guess, in New Mexico, and then the spacecraft team is assembled from all over the world. So Vishnu is going to join us here from DLR, I believe, and tell us a bit about, not DLR, Max Planck. I always get the two confused, so that's on me. Sorry, guys. So welcome. Thanks for spending your evening with us.
Thank you, Brittany.
No problem. Why don't you tell us a little bit about yourself? What's your background? How'd you get involved in this?
I have a PhD in planetary science. Before that, I used to be a science journalist, like any journalist before, I guess. And before that, I made movies in Bollywood. So I went from Bollywood to journalism to planetary science. So I had a different career every few years. And so far, I like planetary science, so I hope I stick around.
Nice. So what got you interested in planetary science? I hear it kind of hits close to home on this particular mission. Yes.
Well, I first looked at Vesta when I was about 15 or so from my house in India. Growing up in India, you never used to have electricity in the evening. So it used to get dark, means it literally gets dark. So you had nothing else to do, so you used to go out and look at the stars. So I used to I started looking at Vesta, with the binoculars, and I used to, make sketch, and I used to track it across the sky over a few days. So I got interested in astronomy, and I always wanted to do astronomy, for a living, but, I was not really good at, let's say, in school. So I kind of flunked out a few courses, went a different route for my career, and then, eventually I decided that, I always like astronomy. I should do that for a living. So I get paid to do my hobby, so I don't feel like I go to work every day. So I just, do have fun.
I completely understand you on that. So let's see. There's a lot of ways to get involved in science, and one of the hardest things actually to do is get involved in a NASA mission because they're pretty competitive, and very few people work on them. It's scattered across the globe. So how did you actually get involved in Dawn?
I got involved in two ways. First is that my PhD advisor, Mike Gaffey at the University of North Dakota, studied Vesta for several years and wrote a lot of papers about Vesta. And he's actually a participating scientist on the Dawn mission. So I'm actually a co-I on that proposal. The other thing is that the PI of the framing cameras, which are built by the Max Planck Society and DLR, which are on Dawn, the PI, Andreas, was a good collaborator of mine for several years. We worked on other missions and other projects. So when we arrived at Vesta, he thought I was a natural choice for this project because I had done a lot of work on spectroscopy before. Most of my work was using ground-based telescopes to study asteroids and tell what they're made of. And I mainly focused on near-Earth objects. So if something was going to hit the Earth, I used to tell what they're made of. That was essentially my job profile. And so I had a lot of experience doing spectroscopy, and Vesta being such an interesting object geologically, it was just a natural choice for me to get involved in this project.
Yeah, so one of the interesting things about Vesta is that you can actually see color variation and spectral variation from the ground. It turns out that planetary spectroscopy, we've known about spectroscopy for a really long time. That spectroscopy is essentially how light interacts with matter, and it gives you a way to do remote characterization of chemistry. One of the things I thought was really interesting about Vesta is that it actually was one of the first places in the solar system that we actually used spectroscopy in order to be able to characterize the surface, which is kind of an interesting history back in the 70s, actually. The first real ties between a planet far away and what we knew on the ground of planetary materials was actually Vesta. Could you tell us a bit more about that? I think we've got this picture that you sent here of a telescope.
Yeah, this is the NASA IRTF. This used to be my bread and butter telescope for my PhD. The good part about it is that although I went for grad school in North Dakota, which is cold as hell, I got to spend a lot of time on Hawaii on top of Mauna Kea. So this is the NASA Infrared Telescope Facility. It's the largest infrared telescope dedicated to solar system science in the world, and it's probably the only NASA facility that is doing ground-based astronomy. And we used this telescope to study Vesta for several years. And actually, the rotation variations that we see on Vesta were first actually detected in 1929. So they looked at Vesta using telescopes in different filters, and as Vesta rotated, they noticed that the color changed, in different filters. So that was the first link to say that not only asteroids were, for smaller objects that are out there, but they actually had variations on their surface as they rotated. And in 1970, using a telescope from the same mountain in Hawaii, we first detected the surface variations on Vesta, and we were able to look at a particular type of meteorites. These are called the HED meteorites. These had the same spectral features as Vesta has, and I think I had a graphic about that. If you can bring
let me just pick that up for you. So let's take a look. Just 1 second here.
I think that's number 4.
Yeah, what does the HED mean?
Okay, HED means Howardite. H stands for Howardite, E stands for eucrite, and D stands for diagonite. So I actually have some samples here I can show. So for example, so Howardite is basically a type of rock that we see on Vesta, and this particular type of rock actually, this is a eucrite actually. So first you have eucrite. So there's a small piece of eucrite right here. I think people can see it. Eucrites are very close to being surface flows. So Vesta is a basaltic object, which means that at one point we had possibly lava flows on Vesta. And most of this activity happened within the first 5 million years after Vesta formed. So when you had surface lava flows, you form eucrites. Okay, they cool really quickly because they're exposed to outer space. And when you have material that cool slightly lower, you form diagonites. So diagonites, something like this. Let me open up the box. So that stands for the D. Oops. Hopefully I don't step myself. So here's a diagonite, this Tatooine. It's a green color meteorite right there. So diagonites are cooling much more at depth. So maybe they come from the lower crust, upper mantle part of Vesta. And Howardites are basically mixtures of eucrites and diagonites. Suppose you have a large impact, like we see in the south pole of Vesta, it mixes up the diagonites and eucrites, and it forms a mixture, regolith breccia. So basically, if you mix these two components, you get pieces of diagonite mixed with eucrite, so you form Howardites. So those are HEDs. In this graphic here, I basically give a rough idea of what we do. We have 3 different ways of studying objects. First is the lab spectroscopy, where we take a meteorite. That meteorite is essentially what I showed you here. It's Tatooine, that's there. We grind them up, put in a lab spectrometer, we get a spectrum of it, and then we do the same thing with the telescope. What we do is we look at sunlight reflected off the asteroid here, in this case it's Vesta, and we look through the RTF, we get a spectrum of it. And we're doing something similar with Dawn, where we have sunlight reflecting off Vesta, but only thing here is that Vesta is resolved. It's not a point source like we see from the ground, and we get a spectrum of it. And so we're trying to compare what we know from the ground, what we know from the lab, with what we get from Dawn. So this is essentially a summary of what we do, at least here in Max Planck.
Really great. So you get kind of a chance with Vesta, right, to do something unique in the solar system, which is to not only look at it with a telescope and then look at it now with a spacecraft, but you also get to hold pieces of it in your hand and try to really understand what it's made out of. What a unique experience.
Yeah, it's pretty interesting because you spend hours and hours looking at data and stuff like that, but then I can just put my hand in the drawer and pick up a meteorite and say like, hey, this came from Vesta. So it's really unique. Before I go, I just want to quickly show you the camera. So we built and assembled the framing camera, most parts of it here. What I'm showing here is a qualification model of the framing camera. I think you have a graphic, you can bring it up. Let's see.
Sure, let's see. Which is that number?
I think it's 9. It should
number
be.
9? Okay.
See if it's 9. I'm not sure. I forgot. Let me see. It
sure, yeah.
Yeah, it's 9.
That one.
Yeah, no, I think you can go back one more. There should be one.
Image 8. Okay, image 8. Sorry about that.
Sorry.
All right. 8. That one.
Yeah. So this is essentially what you see here. Here's the cover door, and that's controlled by this motor. You can open and close it. Here's a baffle, just like you have a baffle for a camera lens. Here's the lens barrel itself. That's the blue thing. You guys can see it. And here is the camera head with the CCD and the electronic box below it. The whole thing weighs about, I think, 12, 13 pounds. It's a little bit heavier than the real flight model. And in the back, you have radiators that cool the CCD and also that cool the camera head. The electronic box itself is attached to the spacecraft, and it's cooled through the spacecraft. Let's see. The lens itself is really tiny. It's only 20 millimeters across. It's about the size of your thumbnail. It has a focal length of about 150 millimeters. So it takes a 1K by 1K image of, that's the size of the image, 1024 by 1024 pixels. Yeah, and we built about 8 of these. So two cameras are actually flying on Dawn. One is actually a redundant camera. We use the other one for now, and in case it fails, we have another camera because we use the cameras also for navigation. We also have 2 flight spares, and we have 2 engineering models, and then we have 2 qualification models. So we have 8 of them, and it cost about 10 million euros to build, and we still have 2 of them, so in case anybody wants.
Nice. eBay, right?
Ta-da!
I don't know about that.
So that's pretty exciting. So you actually get to sit there with all of the pieces of what you're doing. So
yeah.
What's it like to be on the spacecraft, like on the science team, when you're doing observation planning and all of that? It's got to be a lot of work, right?
It is. Myself and Lucille, we are not directly involved because unlike other missions, Dawn is a mapping mission, so we don't have pointed observations. So we pretty much observe whatever goes, whatever we see. But the interesting part is that I think me and Lucille are probably the second or third person or people in the world to actually see the images of Vesta. Usually Pablo, who's our camera manager, sees it first, and he's like, literally, 10 feet from us. So he comes running to call us. So we get to see the images fresh as they come off the spacecraft. So it's pretty cool. We try not to do too much analysis because the data has to be given out to everybody. So, but it's really tempting to speculate what we see every time. So it's pretty cool.
Yeah. So tell me a little bit about that. So when we're looking at a Dawn image, when it comes down, there's still some work left to be done, right, before it's actually useful. I mean, one of the things is that it takes a while, and How many
Right.
people do you actually have working full-time on the mission?
Here, for the camera itself, we only have 3 people working full-time. We have a camera manager and 2 programmers who actually do the sequencing. But it's a very small but dedicated team just for the mission. So we kind of get things done. Once the images come down, we have different levels of data. So depending upon the calibration we perform on the images, and they have different uses. So there's level 1A, which is you get to see the image at level 1A, and level 1B they're starting to be useful for doing science. And like every NASA mission, the data will eventually get to the PDS and made available to the public. But the proprietary period, the science team, the Dawn science team, gets to do science on them.
So tell me a little bit about the differences between a spacecraft camera and like my digital camera, right? Why can't I zoom in on Vesta?
Well, Vesta is really far away. So even with the largest telescope in the world on the ground, it's still only a few pixels across. So the camera we have is not really that big. Compared to a regular digital camera, your regular digital camera is probably more powerful than what we have. I mean, in terms of the detector size and the resolution, you probably have a bigger and better camera, maybe on your iPhone, because it's an 8-megapixel camera, I think. But the fact that we are so close to Vesta means that we get really high-resolution images. And also the fact that for doing science, we need a different kind of CCD compared to what's there in your iPhone, or a regular digital camera. So that's what makes these cameras a little bit special.
So we actually have a question from a YouTube watcher. What other asteroids have collections of meteorites that we study?
What other asteroids have meteorites that we study? So obviously we have Vesta, and we also have some information about the ordinary chondrites. So for example, here's an ordinary chondrite. This is, I think, it's a H chondrite. So these are one of the most common meteorites that we find on the Earth. It is speculated, or it is proposed, that there's an asteroid called 6 Hebe. It's the 6th asteroid that was discovered and numbered and named. 6 Hebe is the parent body of H chondrites. And you have other objects that have been proposed. For example, we have LL chondrites, which are another type of ordinary chondrites. The 8 Flora, there's an asteroid called 8 Flora in the Flora family. There's a hypothesis that the Flora family is the source of the LL chondrites. And you also have other things. For example, you have a meteorite called enstatite achondrites. These are highly reduced meteorites, which are formed in a very oxygen-poor environment. And there's a speculation that these things came from the Hungaria region of the asteroid belt. There's a region of the asteroid belt that is pretty close to the Earth. It's the innermost part of the asteroid belt, and most of these Hungarias are very highly at a very high inclination. So the composition of these Hungarias kind of matches with that of the enstatite chondrites. So there's a speculation. So we have, depending, there's plausible parent bodies and there's possible parent bodies. So there's different levels of it,
But Vesta really is the only one that we have confirmed right now, right?
Right. I mean, we have in the case of Vesta, it's relatively unique because we have the South Pole impact crater, which we think is a source region for the Vestoids. Vestoids are these asteroids that have spectral signatures similar to Vesta, and they're also asteroids that are from the trail in the asteroid belt. They go from Vesta to the resonance, and the resonance is the thing that brings everything into the inner solar system, including the Earth. And we have HED meteorites that have spectra very similar to the Vestoids and Vesta. So we not only have a source on Vesta for the Vestoids, we also have the pieces and the mechanism to bring them in. So,
okay. And then I know you had a couple of results that you wanted to share with us that you've been working on. I know you were lead author on a science paper. Is that correct? Or
Yep. I was a lead author on the science paper.
It's pretty exciting.
Yeah, it was an experience. But most of the mapping work and all the color data was processed by Lucille. So I will pass it along to her to talk a bit about the results.
Okay, well, so actually what we're going to do is we're going to talk to Tom Prettyman really quick, and then we'll go back to Lucille. So we'll come back.
Okay, she can talk about the science results. Yeah.
Yeah, it sounds great. Okay, so next we're going to go to Tom Prettyman. Thanks, Vishnu. We'll be talking with you again in a minute.
Okay.
So Tom is joining us from New Mexico, I believe, from is Albuquerque, correct?
Yes.
And so Tom is actually the principal investigator on the gamma ray and neutron detector that we call GRAND on the spacecraft. So the gamma ray and neutron detector is a little bit different than most of the spacecraft instruments that you've heard of before. Cameras and imaging spectrometers are very remote instruments. They're using CCDs, and they're using remote observations, kind of taking pictures of, if you will, of the light that's reflected back from Vesta from the sun. And so what GRAND is actually doing is a little bit fundamentally different. It's actually getting involved in things that are coming back from Vesta. So Tom, why don't you actually tell us a little bit about your background, and then tell us a bit about GRAND.
Okay, well, thank you very much. It's a pleasure to be here talking to you today from Albuquerque, New Mexico. I'm a nuclear engineer by trade, and I got involved with the NASA Dawn mission back at Los Alamos National Laboratory. I worked in the Space and Atmospheric Sciences group there. And I worked with Bill Feldman, who is kind of legendary in the area of nuclear spectroscopy. He built the neutron spectrometer that flew on Lunar Prospector that discovered evidence for water ice at the lunar poles. So Bill and I got involved in the Dawn mission, and we decided to build a gamma ray and neutron detector. It's a very compact apparatus, and Bill and I are both co-investigators. And I'll show you a picture of the gamma ray and neutron detector. It may or may not come up. There it is. This is not the best shot of it, but you can see it looks kind of like a toaster oven. It's a fairly small device. It does not have any focusing elements. So everything that we see that comes into GRAND is coming in from all directions. So one of the challenges that we have that the optical instruments don't is that we have to be in very close proximity to Vesta in order to make our measurements. Now, if you can pull up a picture, I can tell you a little bit about what our measurements are. And I should also say while you're doing that is that once Dawn was launched, both Bill and I went to work for a company called Planetary Science Institute, which is centered in Tucson, and that's where we are now, and that's where we work on this instrument. So the picture that you're looking at just gives you a little bit of an idea of what information you can get from gamma rays and neutrons. And you can imagine that all objects in space are exposed to energetic particles. Some of these come from the sun, and some of these come from outside our solar system. These are known as cosmic rays, and the ones that come from without are galactic cosmic rays. These have enormous energy, typically higher than what you would produce in an accelerator on Earth. And they're mostly protons. And these protons smack into the surface of an airless body like Vesta, and they interact with the nuclei in the surface, causing them to break apart. We kind of call this a splat reaction in physics. And so that's what you're looking at. You're looking at a cosmic ray coming into a surface and bashing apart a nucleus. And out of that you get these particles called neutrons. Neutrons, as their name suggests, are, oops, we lost it. There we go. Neutrons, as the name suggests, are neutral particles, and they undergo collisions in the surface. Some of them leak out away from the surface to be detected by the orbiting spectrometer, and some of them undergo collisions that make gamma rays. And the gamma rays and the neutrons provide a fingerprint of the elemental composition of the planetary surface. So with GRAND, the gamma ray and neutron detector on Dawn, we're going to be able to measure the abundance of specific elements that are of interest in studying this body. These would include, for example, elements involved in forming silicate minerals like iron, silicon, perhaps titanium. In addition, you also have naturally occurring radionuclides, which is shown on the lower right, like thorium, potassium, and uranium, and we should be able to make measurements of that. So if you go to the next slide, I can tell you a little bit about the data we've acquired at Vesta. Unfortunately, the graphic that's supposed to appear isn't there. I'm not sure why that is, but we have just kind of a diagram of the orbits that we're able to achieve around Vesta. And for Grand, we had to go within about 210 kilometers of the surface in order to get our data. And we had to stay there for a long time. And we certainly are thankful for the engineers at JPL who were able to very cleverly get us into this low altitude orbit and keep us there for such a long time. So we stayed there for about 4 months. And we're still analyzing the data. I don't have any results to report to you today, but I'm hoping that we'll be able to talk to you about the elemental measurements soon. So go ahead, Brittany.
Yeah, so I wanted to ask you, what are, so this instrument, since it's so different, you can actually kind of get in and really do the hands-on chemistry. What are the reasons why we chose to fly a gamma ray detector on Dawn instead of maybe just doing a spectrometer or just doing something else? What's the special information especially relevant for this mission?
Right, and I think the best analogy is to Lunar Prospector, where we're able to globally map the abundance of all the major elements and radioactive elements, rather, on the Moon. And it provided us a complete picture of the elemental composition of the Moon. The elements make the minerals. The camera and the reflectance spectrometer measure some aspects of the mineralogy. And so the gamma ray and neutron detector is complementary to them in that they measure the actual constituents of the minerals that make up the surface. And that's very important to understanding different aspects of how Vesta might have evolved and how its surface was shaped with time.
So something I'm really interested in, we're talking today about Dawn departing from Vesta. It's headed on to Ceres, and really I feel like Grand might be one of the stars of the show when we get to Ceres. And I thought you might want to share with everyone why that is.
Well, I think that all of the instruments are going to be stars, but Dawn is a team first and foremost. It's not one instrument, and we all work together to produce a beautiful result. So what makes Ceres different from Vesta is that Ceres is thought to be water rich. And the processes that shaped Vesta's surface were magmatic processes. So think of it as a world that got heated up and melted and then cooled again. Ceres was probably formed cooler and contained a lot of water. And as such, you would have all kinds of different water chemical reactions or aqueous processes that might have gone on that we might see on Ceres' surface. There are papers that speculate that Ceres might harbor a subsurface ocean, which would be fantastic. And if it did, then you might see expressions of this on the surface of Ceres. And the chemical signatures from these aqueous processes would certainly be visible by Grand.
Yeah, that's one of the things I'm most excited about, actually. As we know, originally Dawn was going to have a magnetometer, so one of the ideas was that potentially Ceres might have an ocean or might have had an ocean at one point in time, and so we won't have the magnetometer to get there. So I'm kind of excited to see the hydrogen results from Grand, or when we get there, that might actually be able to tell us about the water composition. So I'm a little bit biased. I'm kind of into ice, so I'm really excited. I certainly love Vesta, but I'm really excited about that potential when we get out there. So yeah, let's see. Do we have any questions about Grand out there? You've got one more image actually to show us though. You were mentioning that it's a little bit different than an imaging camera, and so this is kind of how the spatial resolution works for that particular instrument. And it's basically the distance from the surface controls what you see, right?
Right, and what you're looking at is an image of Vesta, and superimposed on it in different colors are the regions that Gran can see from one point. And it's a fairly broad portion of the surface, unlike the cameras, which can focus in on specific locations. We're seeing fairly broad regions. I don't know if you can play this. It's a movie. It actually shows the orbit maybe you can't show it on your computer.
I can probably get it up on mine. Let me try to do that for you.
Sure.
Let's see. Oh, actually, I'm not sure that we have. I don't think that I actually have the. Oh no, yes I do. 1 second. Let me just show that to everyone. New operators. So let's get that video. And let's go ahead and play that. 1 second.
Okay, good. So I guess the point that I want to make with this is that we're looking at broad regions of the surface. We're looking at the whole surface. The cosmic rays don't care about sun illumination, so you see every part of the surface of Vesta, but you see it at a fairly broad spatial scale. And what you're looking at is the spatial resolution of the instrument as we fly over it in a low altitude orbit. And you can tell from the picture that we can resolve features that are on the scale size of the big basin in the southern hemisphere of Vesta.
Great. Well, thanks. So actually, Tom, just to wrap up, I wanted to ask you about making a transition from nuclear engineering into being a planetary scientist. How does that work exactly?
Well, it's kind of a tortuous path. I've always been interested in astronomy, and I kept that interest into adulthood. I was also interested in nuclear science and really enjoyed working on and building radiation detectors and applying them to a wide range of applications. My first job after I got my PhD was actually to work on the design of oil well logging tools, which use radiation to characterize the subsurface of the Earth for exploration purposes. And I've always been interested in science and exploration. So for me, it's just been a joy, and I particularly appreciate the many talents that have to go into these missions in order for them to work. There are many disciplines represented, planetary scientists, aerospace engineers, and a few of us are nuclear engineers too. So it's quite a lot of fun.
And we actually got a really relevant picture or a question from online. So, what since you've got this interest in exploration and in the elemental composition, what do you think about these idea of mining asteroids, about planetary resources?
Well, it's like a lot of ideas. I think it's interesting. I think I saw a report once that estimated the value of a iron-rich asteroid, and I was astounded at how much it might be worth. But I'm scratching my head a little bit as to how one might return that iron, or how one might use it. So it certainly is interesting. Of a iron-rich asteroid, and I was astounded at how much it might be worth. But,
looks like Sammy just joined. There we go.
One might return that iron.
Hey Sammy, can you mute your feed?
So
all right.
Me mute.
Of a iron-rich asteroid.
It's not letting me mute.
Okay, there we go.
There we go.
All right, so you're saying it might be difficult to figure that out. I've actually been thinking about that too. How would we bring materials back? Because when we talk about mining or subsurface exploration on the Earth, when they're when they're differentiated, you're looking for a mine, a concentration of it. Some of the asteroids they've been talking about mining, they're talking about asteroids that never really melted. So I wonder how we would know exactly where to go and concentrate that stuff. So do you envision strip mining, or is it going to be melting everything down and sending it back?
I think that's presently far beyond my present ability to envision, but it sounds like people are interested in it.
Yep, definitely. I think it's an interesting thing, especially now that we're starting to really explore these bodies with spacecraft, and hopefully soon with people too. So. Well, thanks, Tom. I know you probably have to go fairly soon. I really appreciate you joining. Thanks for telling us about GRAND. We look forward to upcoming results, to seeing you guys check in. So with that, thanks very much. And we're going to go over and talk a bit with Lucille LaCour. So Lucille is also a member of the framing camera team. She's there in Germany. Same location as Vishnu is, actually. So, hi, Lucille. Nice to see you. So, why don't you tell us a little bit about your background? It's a little bit different from everybody's so far. It seems that so far there really is no one path for becoming a scientist on a NASA mission, is there?
Yeah, that's true. So, actually, I did a first master in planetary sciences, and then I went on a PhD. So, I did my PhD on the Cassini mission. Actually, I worked mainly using the VIMS data, which is spectral data, and also radar data to study especially the surface of Titan. So I was interested in the geology of Titan, which is kind of a tricky thing because Titan has a really thick atmosphere. And then I worked 1 year on Mars data to study the geology of Mars using the HRC camera. So it's the high resolution stereoscopic camera, stereo camera, and so it was to study ancient, I would say, ancient outflow channels, so where water has been flowing. And finally, since November 2010, I'm in the Dawn team, so specifically in the Dawn framing camera team. So working on the color images and also clear images of Vesta.
So that's pretty amazing that you've already worked on, what, 3 different missions now? And,
yeah. Myself, I'm still amazed by that. But it's pretty interesting, pretty cool.
There aren't like a ton of young women actually working on a lot of these space missions. It's kind of a unique setting. So that's pretty cool that you've been able to accomplish that. So, So I also hear that you have some outside interests that we share in common, horseback riding, for instance. How do you fit horseback riding in between all the science that you've been doing?
Fortunately, I still have some free time in between the image processing, so I can ride sometime in Germany here when the weather is nice.
So tell me a little bit about that image that's actually behind you on the wall. You've got a big picture. It's got science on the background.
So this one is actually the science cover. So we prepare because we had the paper in Science about the albedo and color analysis of Vesta. So then we prepare this cover using Hubble data. So it's about 60 meter per pixel resolution. And we assembled it and then send it to the magazine. So we have this nice picture of the Marcia crater. So it's one of the actually most impressive crater after the South Pole Basin. So it's called Marcia and Calpurnia and Minutia, I think. So it's called the snowman craters.
Yeah, the snowman craters are probably everybody's favorite feature on Vesta. Really kind of a fun thing. So you mentioned albedo and color. So what does albedo mean, and what is color telling us about the asteroid?
So we receive the color data. We have 7 color filters. So we process them. So we obtain the albedo of Vesta. So it means that we correct for illumination effects So like emission angle, incidence angle, so the way sunlight is reflecting on the surface. And once we correct for that, then we have what we call the albedo maps, and we can then analyze specifically, try to infer physical properties of the surface, like grain size or composition. Actually, for doing this, we need to compare the color data with meteorite spectra, for example, from HEDs.
Gotcha. So you're basically taking all of the parts of the visible and infrared spectrum and kind of putting them together to tell us what Vesta's made out of, correct?
So let's say that the framing camera is complementary to the VR instrument. So we can have a color spectra, but we can have color spectra of the surface to infer composition, but we don't have as many channels as the spectrometer itself, which is more dedicated to do this kind of analysis. But the thing with the framing camera is that we have a really good spatial resolution, so we can see really precisely what kind of geological units are on the surface and what are their colors or their composition and their textures, things like that.
Yeah, so we've been talking a little bit about how complementary all of the Dawn instrumentation is. That's really why we selected the set of instruments that we have on the spacecraft. So can you tell me a little bit more about what it's like to use two sets of data from the same spacecraft, really to put something together and understand Vesta a little bit better? How does that work, and what else do you have to do in order to really understand things?
First, we can select some sites, interesting sites we see from the camera images. So we have some clear filter images that covers pretty much the entire surface. So using that, we can select sites and try to study the lithology or the stratigraphy of the surface. So which units has come first. So we have some, for example, bright materials and dark materials. We have also some debris flows, especially on the Marcia crater. So once we define the geologic settings we are looking at and the feature, then we can either do chronology using crater counting or do mineralogical analysis using the spectrometer data. And then with this spectrometer data, we can either compare to meteorite data from the lab, or do some modeling of the spectra.
Okay, so you can just make that integrated picture. That's pretty cool. So I noticed that when we were testing the VR instrument, actually, one of the ways that it got tested was that they actually powderized samples of the HEDs that we'd been studying in the laboratory, and then actually took spectra of those, right? So we actually got kind of a chance to do that, and then we've got this beautiful color image that you shared with us.
So this red one is an Opia crater. So this is a really interesting crater on Vesta. So actually there are two craters like that on Vesta, the Octavia crater and the Opia crater. And they both have a really, I would say, particular ejecta blanket in the color data. So this one is not the same as the previous one. It's a color ratio composite images. So here we use ratios of color filters to really brings out the information due to the properties of the surface, like mineralogy, for example. And this crater is actually on a slope, so it's not it didn't impact on a flat surface. It's on a slope, so that's why we have a really asymmetric ejecta distribution. And compared to all the other small fresh craters we see, for example, at the bottom of the image, we have a really bright yellow fresh crater. This kind of crater has red ejecta and are not as bright. So it's probably a different composition. So that's what we're trying to investigate here. And it has a really red visible slope. So that's why it's showing up on red on this color composite. So we think it could be some kind of impact melt or material that has been excavated from deeper on the surface.
What do you mean by a red slope? What does that mean to astronomers?
In this case, we have actually compared the color information of this unit, this ejecta, to the global average color properties of Vesta, and we see that the color spectra, actually the average color spectrum of this unit, has a redder color, meaning that the slope in the visible is steeper. So usually on the moon, when we say it's redder, there has been more space weathering, so the material is more altered. So it's some kind of global effect on the surface of an object. In the case of Vesta here, it's really localized, so we think it's something else involved here, another process that is giving this red color.
Yeah, so it's maybe that you're churning up material in a little bit different way and seeing some more of the composition, right? That's kind of where using these two instruments together really helps. So so the blue is kind of the average then, and then the red is the stuff that's maybe more rich in other stuff. That's pretty cool. So you had another instrument as well, right? Or another image as well, another color composite?
I have the global mosaic, actually.
Oh, the global mosaic.
So it's the South Pole mosaic, probably the image number 5. So.
Ready 5?
I think. So here at MPS, we basically process all the data, clear and color filters, we calibrate it, and then we build mosaics from it, so we can wrap it on a shape model. And we have an idea of the global properties of Vesta with that. So I don't know if you can see it now, but okay, so it's basically centered on the south pole of Vesta, and you can see that the rare Sylvia basin, which is almost centered on the center of the image, appear much brighter than, much like yellowish and brighter than the rest. So it could indicate that it's a different composition or it's fresher material. And you see actually that this particular basin has also ridge and groove terrain, so it has been beaten up, and then you see the part of the rim also showing up on the right side, really bright.
Yes. One of the really interesting features on Vesta, right? Is that this giant impact in that south polar region was something that we saw with Hubble, and to see it up close, it's both kind of what we expected to see, but also completely different. And the composition here is telling us something too, right?
Yeah, actually, from HST we could see already some variation with a low spatial resolution, but then when done right, we discovered that it was actually much more impressive than we thought. So a lot of different color units, and of course we could see at really much better the different units. So like the Opia crater with the red color, and then we could really associate the different fresh craters with the color, and then the rest of the basin with another type of color.
That's pretty great. Yeah, so thanks for sharing that with us. I think it's a really amazing perspective of Vesta. You guys also set in a couple of movies, is that right?
Yeah, we have 2 videos. So it's to show some material that has a really dark color. So video 1 and 2, and you have the Dawn team named them the Tolus because it's dark materials that we find on some kind of hills that they are quite particular.
Oh, okay. So I guess we're having some issues playing the video, but we'll try to get those up later, and maybe we can discuss it afterwards.
Okay.
All right. Well, thanks so much. I will come back and we'll try to play those videos here a little bit at the end. We're going to go on and talk to Sami Esmar about what it's like on the inside of Vesta. So thanks for showing us a little bit what its surface is about. So let's go over to Sami. First of all, hi Sami, welcome. Let's see if we can unmute Sami. Let's see. Oh, okay, so I think Sami, if you look up to your corner, just need to make sure that you've clicked on your sound.
Can you hear me?
Yes.
Yep, there we go. Great. So
A lot of buttons in this.
yeah, there are. It takes a little while to figure out. So Sammy Asmar is the lead for the gravity science team there at JPL as well. So Sammy, why don't you tell us a bit about the gravity science and how it's done and how you got involved?
Uh, okay, I'm actually technically not the lead for the gravity science on Dawn. I am the chair of the gravity working group, but the gravity co-investigator is my friend and colleague JPL Alex Konoplev. He was on the original selection team. I was not, and then at some point he needed help and recruited me to join the mission. And then Chris Russell, the PI, invited me to be the chair of the gravity working group. So obviously what we do, Alex and I, is study the gravity of Vesta, and we'll do that at Ceres as well. And I'm going to talk a little bit about why we do that and also about how we do that. The why is that most people on Earth think of gravity measurements as one number. We say there's little g on Earth is 9.8 meters per second square, but in fact gravity changes depending on the location of where you're sitting or standing on the planet, any planet, or any asteroid. So the collection of values that are a function of the latitude and longitude are collectively called the gravitational field. In fact, we express that mathematically in a more complicated formulation called spherical harmonic expansion. But the reason we would need to study the gravity of any celestial body is to really know what's it made of on the inside. Because from gravity or gravity field, we can tell what is the mass and the mass distribution within the object. And from that, we can kind of peel the layers of the onion and go from the crust all the way to a core and find out the structure of the body. The way we do that, any questions so far?
Oh yeah, I was just saying that's one of the really important investigations that Dawn has been doing actually at Vesta is that based on the chemistry of the HED meteorites and based on Vesta's shape, we kind of thought that perhaps it was differentiated, but we didn't really know exactly how well and exactly what that looked like. And so that's one of the investigations that the gravity team has been undertaking is to try to figure out exactly how big the core is and how deep the mantle is and things like that, right?
That's exactly right. And you mentioned a key phrase, which is knowing the shape of Vesta. So to really process gravity data properly, we also need the second sister data set, which is the shape of the body. And although Dawn does not carry an altimeter to carry out classical measurements of altitude and shape, the imaging team has done a fantastic job gaining or producing the shape of Vesta just from camera images. So in fact, now we have a nearly complete shape of Vesta, and we can correlate this shape information, or call it topography, with gravity. And that's how you can then really find out what is subsurface. Because you can make a gravity measurement at a specific location and not know the source of that gravity signal, what mass anomaly is causing it. You would not know until you also have either images of the surface or topography of the body.
Okay, go ahead.
You're looking now at a graphic of the shape of Vesta. It is slightly out of date. At the time of this image, the sunlight had not hit the northern polar region of Vesta, so we're still lacking images there and therefore lacking shape information. We have since then filled in most of that, but I happen not to have an up-to-date image handy. So we correlate this particular called a map, which is a shape model, with another type of map, which is a gravity map. And you're now looking at the gravity map. And for people not familiar with this, this is contour information on Vesta that represents the highs and lows from a gravity point of view. If you were wearing gravity glasses, say, this is what you would see. We also have in the corner the same view looking from the South Pole region. which is of particular interest to the Vesta science team because of the shape there at the Rhea Silvia feature. So by combining the gravity and the topography again, we have deduced that Vesta is indeed differentiated, and we have a model actually. It's a working model, could be challenged in the future, where we actually, like Earth, we have three layers. We have a crust, a mantle, and a core, with obviously the core having the highest density, and the mantle the lower, and the crust with the lowest density. And this model seems very consistent with our gravitational data. So it satisfies our conditions. And we're working with that and on the verge of producing some publications.
So can you explain to us kind of what the shapes on this particular figure are showing us? It's kind of loby, and you're seeing some red areas and some blue areas. Can you explain to the non-expert what those kind of shapes are maybe telling us, or what they might be associated with?
Yeah, so just to know how to kind of read or interpret such a figure, the blue region is low gravity, and the red region of the other extreme is high gravity. So if you're flying over a feature that shows red on this image, the spacecraft will literally get pulled towards that feature. There's a gravitational attraction above average. So if we call that location between yellow and green, where we call that the average or nominal gravity, red would be particularly high. So that means either on the surface or beneath the surface, more likely, there is some mass or there's some material of higher density than its surroundings, and it's producing additional gravitational force locally. The opposite is true for the blue regions, where you have the absence of mass like this, and the spacecraft will feel what we call a negative gravity signal. In fact, it will physically move away from that, but these analogies of moving closer and moving away are very small, so I don't want people to get the image that's very high perturbation. They're very small, but our instrumentation are so accurate that we can measure these very small changes. For example, to think of this geophysically, if you fly over a region and it's red, so it's high gravity, you would think, okay, there's more mass, maybe it's a mountain. And then you look at the topography, and in some cases, there would be a mountain and you're satisfied. And in other cases, it might be flat, in which case you start scratching your head. Why am I seeing higher signal, but the topography is not special? And that's when you deduce that it's a subsurface embedded material of higher density. So right away, you can start looking below the surface. This is probably the only method of probing subsurface structure of any planet. One of two methods probably, the other one being magnetism. And that's because both gravity and magnetism are forces that are created on the inside, but have a manifestation on the outside that could be detected by a spacecraft or an observer.
Yeah, one of the things I think is really interesting about this picture is if you look at the South Pole view, you really do see that there's kind of a big gravity low right about where that South Polar Impact Basin is. So that's pretty interesting. But it's also kind of a weird shape, right? You don't actually see the rim going all the way around. Is that a resolution effect, or is that because it doesn't really look like it's there?
No, our current interpretation is that the ring feature is incomplete. It was probably created at a certain time in Vesta's geological history, and after that another impact or another event took place that buried portions of the original basin. So
Yeah,
that when you start actually getting chronological timing of events from a figure like this.
Yeah, that's pretty exciting. So basically, you're using this to be able to see inside Vesta and be able to tell a little bit of its history that way. So really interesting, especially when you compare it to the topography and the shape as you discussed. So what is different or the same about Vesta versus other objects that you've looked at with gravity data?
The interesting thing about Vesta is that it is turning out to be rather similar to other objects we've looked at, not different. So we've looked at mostly planets and large moons of planets, including our moon and those around the giant gaseous planets. And in most cases, we're seeing the typical differentiation into a crust, a mantle, and a core of some sort. And we were, I don't know if I should say surprised, but we had not really appreciated, given that Vesta is a small asteroid, although it's one of the bigger ones, but it's smaller than the planets, that it has also differentiated in the same manner. So it was actually a big discovery from our point of view that Vesta is similar to the planets, and that's why a lot of people are now calling it a protoplanet. So its age is old enough that it had allowed, that the age had allowed the asteroid to differentiate. So that's very interesting.
Yeah, I actually had a question here from a member of the public that says, do we all agree that Vesta has what it needs to be reclassified as a maybe as a dwarf planet? What is the gravity telling us about that particular discussion?
I think gravity would lean towards that, but as you know, this is such a hot and controversial set of criteria for how one does that. So that's a kind of worms to open. But I think from a gravity point of view, by all means, yes, it is closer to a planet.
Yeah,
it's just not a single rock out in space. It's
a pretty amazing place. So this is a pretty cool perspective, and I think it's neat that you get to study kind of everything. You get to study how Vesta formed and what's happened to it since then, all from gravity. So
it's a very powerful technique, very powerful tool, and a set of data. And again, it is one of the few ways, short of drilling into a planet, of discovering the interior structure.
Yeah, this is pretty great. Well, thanks so much.
I want to just add very quickly that the beauty of this is the simplicity of the instrumentation. It is very accurate, but it's relatively simple in the sense that we're utilizing the radio links on board the spacecraft that are used for just normal communications. And we actually monitor precisely the changes in the Doppler shift as it flies around Vesta to deduce this set of information about gravity. So it's basically we're taking advantage of an existing radio link, and from that producing a powerful data set.
So we've got one more question before we move on, and someone has asked, so are those red regions maybe a little bit like mascons on the moon? Have we seen any evidence for something like that?
So on the moon, we have indeed discovered mascons actually a long time ago, and what these are regions where gravity and topography anti-correlate. So you would see a gravity high, but topography low, and then you would deduce that there's a subsurface material, either lava flow in the case of the moon or an embedded impactor. In the case of Vesta, we've actually looked for that, but we are yet to conclusively say that any of these are mascons. We're still finding sufficient correlation with the topography that we're getting a lot of explanation from surface features in most of the cases. We're not done completely, and we might still discover a mascon, but we're not there yet.
Sounds great. Well, thanks so much for joining us, Sammy. We're going to go on and talk now with Deborah about some other surface features. Thanks so much for sharing a part of your day with us, and congrats on the great work that you're continuing to do here with Dawn. And I look forward to maybe seeing you at a team meeting in the future. So take care. So Deborah, let's wind it up. So Deborah's joining us from APL, correct? So in Maryland, and we'll be talking a little bit about some of those really enigmatic features on Vesta's surface that are actually, of course, some of my favorites, the ridges and troughs. So Deborah, why don't you tell us a little bit about your background, what you've been doing, and how you got involved in Dawn?
Background, okay. Be good if you could hear me. Can you hear me?
Yep.
Okay, good. So my background, I have actually always been interested in space. I giving away my age here, but I was a little kid when Viking went to Mars, and I thought those pictures that Viking sent back were the coolest thing ever. So, you know, probably as young as 6, I wanted to study outer space. So my bachelor's degree is in astronomy, and it was somewhere while studying astronomy that I realized that planetary astronomy was my favorite part. So when I went to grad school, I did geology, and as somebody with an astronomy undergrad, I had lots of math and physics. So when I was taking geology, the kind of geology that really appealed to me was the most mathy and physicsy geology, which happens to be structural geology. So I'm actually a structural geologist, which means I study things like faults and fractures and tectonics in general. So as I started working in planetary sciences, I was studying faults and fractures on Mars and Venus. And then after I got my PhD, I had got a postdoctoral job at APL, working for another structural planetary geologist. And I created a structure map of all of the linear structures on Eros, which is a much smaller asteroid than Vesta, but is also an irregularly shaped body. So unlike everybody else who's talked today, I actually am not on one of the instruments. I'm a participating scientist on the mission, and which basically means that as the mission was approaching Vesta, they asked for other scientists who were interested in studying Vesta to propose a type of research that they would do, and these were all evaluated. And because of my experience with mapping linear structures on an irregularly shaped body, I proposed to do this on Vesta, and luckily for me, I was selected. So that's how I got into doing the Vesta research.
So you wrote a special proposal, basically. So the way mission teams usually work is that a group of scientists gets together and they come up with an idea and they go through many rounds of proposals. Our mission actually began with Chris Russell and a harebrained idea in about 1994 to use an ion engine to get somewhere, and it was the asteroid belt that he was trying to get to. And then it got proposed in many forums and different teams and different instruments. And then when Dawn was finally selected, all of those scientists stay with the mission the whole time. And then because these missions take a really, really long time to go, then newer, younger scientists and new perspectives and more people to do the work are needed. And so these participating scientist opportunities are a way to get involved. So that's pretty exciting that you actually, congratulations, by the way, on getting selected. That's a pretty competitive process. So, so tell us a little bit about what you've been doing on Vesta that's so interesting.
Well, so every asteroid that's been visited to date has had some kind of fault or fracturing. But on all of these other smaller asteroids like Eros and Ida and oh gosh, I'm blanking on names. Everything that was visited before Vesta, these were just, for the most part, very small features, which isn't unsurprising given the small size of the asteroids and the fact that they're really just rocks in space. When we got to Vesta and we started approaching and those first few pictures we were seeing as we were getting close, we started seeing these huge, monster-sized fracture systems, these features that are called troughs. And if you go to the image that should be showing up now, you can see these. These are right at the equator, and they're these large, see, I can't bring it up.
It's
there you go. Okay, these incredibly large fractures, and I mean, you actually will find a lot of people who will refer to these as grooves. And this is kind of left over from studying other asteroids where you've had something that would be a groove, which a groove is this very small little feature. It's kind of like a tiny little, just this little kind of scratch in the surface of an asteroid. These are not grooves. These are huge Mongo Grand Canyon-sized features. And so I started with mapping these features out, and actually Lucille was doing some mapping of these features also, because she was doing the quadrangle mapping of some of the largest of these features. And the difference being she was doing a geologic map, and while I was mapping them, I was actually trying to determine things like whether or not there had been like displacement along the surface. So in a fault, it's not just a simple fracture where something cracks. You would actually have a motion down the fault plane where something is actually either going up the fault surface or down the fault surface. And in my analysis, we were able to actually determine that these are a kind of faulting that occurs when pieces of rocks are diverging away from each other, and you get downslope motion along the fault face. So these have quite a bit of displacement, and actually the largest of these features, which you can probably see if you look along the feature, there's one that really pops out. It's the longest, it's the widest, it's the deepest, and it is just about the size of the Grand Canyon. It's a little bit larger, a little bit deeper, a little bit wider, but you know, it's effectively the Grand Canyon, and then there's all those other ones to the north and south of it. So if anyone's been to the Grand Canyon, try and picture that. Because this is, you know, it's an asteroid, as everyone said, about the size of Arizona, which is where the Grand Canyon is, but the Grand Canyon is not, you know, taking up half of Arizona, and these features are. Now if we go to the next image,
I was just going to say, I think it's really interesting that we've got the Grand Canyon here on Vesta. Some of the comparisons that we've been able to make between Vesta and other planets are that impact structure at the South Pole has the second highest mountain in the whole solar system, actually taller than Mauna Kea and just smaller than Olympus Mons on Mars. And it's this really small little planet out there. So it's got its own Grand Canyon. It's comparable in size to our own Grand Canyon. To maybe, how does it compare to Valles Marineris, for instance? Do you know that?
You know, off the top of my head, I do not have Valles Marineris's size, but Valles Marineris is about the size of the United States. So it kind of goes from California to Maryland, if you think about it. So Valles Marineris is considerably longer than Davalia Fosse, which is the largest of those features I was just showing you at the equator. But if you look at the image we're seeing now, this was actually a second set of troughs that were identified as we started getting more northerly images. You can see it. So there's the snowman, and just to the north of the snowman, there's another big trough. This one is actually shallower than what we were looking at the equator, but it's wider and it's actually longer. And it's basically, you can probably see that there's far more crater on top of this fracture set. So just looking at it, geomorphology and what's happened to it, we could determine that this is probably an older set of troughs. So very similar to what we're seeing at the equator, but older, which meant, like for example, the reason why it's probably shallower is that there was downslope motions, these like little landslides that we're seeing on all this lumpy surface of Vesta, and these were kind of eroding away the walls and filling in the bottom. So it became wider and wider and shallower as this kind of erosion occurred.
So we have a question from the public that's actually, how deep are the troughs? Do you know, what's an actual measurement of one of them?
Davalia Fosse, the largest of the equatorial troughs, has a maximum depth of 5 kilometers. It's quite deep.
So
for an example,
deeper than the ocean.
Yeah, Grand Canyon's only 1.8 kilometers deep. Davalia Fosse at its deepest, and it is not that same depth all the way along the trough, but at its deepest it's 5 kilometers. Saturnalia, which is the northern trough that I was just showing you, has a maximum depth of 4 kilometers in its main part. There is a section to the south that I suspect is a continuation of that same fracture set, but that one is much deeper. But I think it was probably affected. This section of Saturnalia is closer to the equatorial troughs, and I think that the formation of these equatorial features kind of reactivated faulting in this area, so there was more motion along that particular fault while the equatorial faults were, you know, doing their thing.
Yeah, do we have an idea of how old these features are?
It's been really hard for people to try and date these. It's hard to date an event. I mean, we have ways of dating geologic units, and it's called crater counting. And basically, we have these people who count every last crater, and they have magic lines. It's basically, we can come up with really effective dates for this because we have absolute dates on the moon. And so people have been able to do this crater counting, and then we have samples from the moon, and they've been able to come.
Oh.
Uh-oh.
We lost her for a minute. Well, we'll try to get Deborah back. But I think that was actually a really great segue, actually. So Deborah was mentioning the difficulties in age dating all of these features. And some of it is that depending on the person you talk to, all craters are not created equal. And so it's somewhat difficult sometimes to be able to determine what the real age date is. So we mentioned at the beginning of this hangout that we just launched the Asteroid Mappers interface. You can actually go over to CosmoQuest, to the CosmoQuest website, and get a chance to go ahead and practice. It's cosmoquest.org/mappers/Vesta, and that is actually a place where you can help participate in trying to answer these questions. Vesta, we thought, would just be covered mostly by impact craters. I'm kind of partial to the ridges because part of my thesis was thinking about would there be text. Welcome back.
I'm so sorry.
That's no problem. I was just mentioning to people that one of the surprises from Vesta has been to see these features and see so many of them, and that one of the great things that Asteroid Mappers, that the CosmoQuest and the citizen science effort that we're doing to help do crater counting and help learn how to map the surface of Vesta will actually probably try to help us answer this question of really how old these features are when they happen. So it's a chance for the public to actually get involved in exactly this question that you were talking about.
Well, the one way that we might be able to date these, it's very difficult, as I was trying to say before my computer cut me off. Lost my internet connection. That's what happened. So it's really hard to date, like I was saying, a fault face remotely like this. But there's another analysis that I've been doing, and this was actually published in another one of the science papers, like Lucille's and Vishnu's that they were talking about earlier, a paper that was first authored by Ralph Yeoman. We discussed the analysis. If you had a fault here on Earth, a geologist would go to that fault face and they'd slap a Brunton compass on it, and they'd be able to determine something called strike and dip. And basically this is the orientation and the angle of faulting of that particular fault. Well, we can't do that on Vesta. As much as I'd love to, I cannot walk up to these fault faces and figure out strike and dip. But what I can do, because this is an irregularly shaped body and these are really long features, and we have this lovely shape model. Sammy showed the topography of Vesta. So I have a tool that allows me to map right onto the shape model. And so basically I'm getting three-dimensional data as I map out one of these features. And then I can model a plane that this feature creates that cuts through the asteroid. And this is a similar analysis that I did on Eros, and we were able to use this analysis on Eros to figure out what was forming the various features. Well, when I did this analysis on Vesta, very interesting thing that came out is that when we mapped out all the equatorial troughs, basically it indicated that they were all being formed by some event that was occurring basically where the central mound of the Rhea Silvia impact basin is. So that's this giant impact at the South Pole. And then when we did a similar analysis of those northern troughs, they all had a center of formation that actually corresponded to the second older impact basin at the South Pole, the Venina Basin. So basically I was doing this analysis before we knew there was a second basin there. So as I was doing this analysis and wondering what this second point of formation meant, Paul Schenk, who's another participating scientist on the team, was looking at the South Pole and saying, you know, guys, I think there's a second giant impact basin down here. And we basically, like, we're presenting this at the same group telecon. And it was like, whoa, eureka. So my point here is because we have this suggestion that these two sets of features might have been triggered by these two giant impact events, that means that they would be similar in age to the giant impact events. And unlike doing dating of a fault, it is actually possible to date the impact events. They have large floors, and so you can do this crater counting on the floor and come up with ages. I don't think that we had, as a team, have agreed what the age is yet. There's a little bit of there's some wiggle room, and different groups are coming up with different ages, and we're refining that process and coming in towards an established date, but it's still a work in progress, and frankly, I don't know what those dates are. But in this process, in this way, we should be able to determine what the age of these fracture sets are.
Yeah, I'm really excited about that, actually. I'm one of the people that started thinking about what this surface might look like as part of my thesis, actually. So I was a graduate student on the Dawn program before we actually got to Vesta. And so this is one of the things that I was thinking about, was what would happen if you smacked Vesta really hard. And so figuring out these ages and stuff is going to be really exciting for trying to understand really what process is forming them. So I'm just really excited to see all the members of the team, and I was thinking about it, and it seems like your experience actually with smaller asteroids may actually come into play. We've discussed a lot about how Vesta is very much like a planet, but Vesta is also like an asteroid. It's relatively low gravity, and we see all kinds of evidence for surface flows of just material falling down slopes. And so I imagine that kind of seismic shaking and movement of material really kind of makes the aging by craters very complicated. We see that on other asteroids. So it'll be really interesting to see if we can kind of pull that effect out and know if we're looking at a raw date, or if we're looking at a resurfaced impact crater from seismic shaking from other events. So really kind of an exciting thing. One of the things that we've learned is that the science starts now. When we're in operation mode around a planet, there's so much work to be done just to make sure the spacecraft is flying right, and make sure the instruments are working well, and that we're getting the images formatted in the correct way to get it out to the public, that a lot of the analysis, we just kind of cut off the cream of the crop right there at the top, and then don't get a lot of it until we've already departed. So this is just an example of some of the really great science that I'm sure is left to come. So what's your next step, Deborah?
Well, I've been doing some modeling, like you said. So this analysis I was just discussing would imply that these giant troughs were formed, or at least triggered, by impact. And this is something that we have observed on other smaller asteroids, where you get grooves that form around either radial to or circumferential to an impact event. But these features on Vesta are significantly different in morphology from what we would see on a smaller asteroid. And so there have been several people doing models and coming up with different aspects of the impact event on a Vesta type body, and what this might mean for fracturing. And the modeling I've been doing has actually been looking at the fact that Vesta is differentiated. So basically, if you have a giant impact into a differentiated body, there's a lot of density differences as you go towards a core. So you have this iron core, and then this kind of viscous mantle material, and then a brittle crust. And that is actually going to have different implications to the stress regime than if it was just a homogeneous small asteroid that's made up of all just one kind of rock. So by doing this modeling, yes, these troughs might have been formed by an impact event as if it was a smaller asteroid, but it's the fact that Vesta is this more planet-like body that I think is what is resulting in these giant troughs and showing us this particular shape that we're seeing in these features. Yeah, I'm looking really forward to actually figuring this out. It's one of the cool new questions that wasn't really expected, and it's kind of fun when you're in planetary exploration. You have a set of questions and a set of hypotheses that you go out to test, and invariably, when you get to the body, you see a whole new set of questions. So I have one more image if people want to look. It's a very rough map, and all it shows is the equatorial troughs in relation to the orientation of the northern troughs. So in black, you have the equatorial troughs, and it's just a few of them. The largest ones are there. And then in white, you can see the lines of Saturnalia Fossae in the north, and then associated fractures, and those dashed lines that are in white are that's where I think Saturnalia Faucae is actually continuing to the south. And I've labeled a few craters here. Marcia crater, which is the southernmost of the snowman craters, because everybody loves the snowman. But this is just so people can get a sense of where things are oriented on the asteroid. And I also outlined Vestalia Terra, which is a favorite feature of mine, but not something I've published on yet. So
I have my favorite idea for that one too. So, all right. Well, I wanted to thank everyone for showing the images, and just to kind of close up, I was going to introduce everybody to the thing that I'm looking forward the most to. So we've just left Vesta, but we're looking forward to actually coming out and seeing Ceres for the first time. So I wanted to show you kind of a fun image that I put together actually for my thesis defense. We've seen a couple different versions of these figures showing around. And so this is actually a picture of Ceres, Vesta, and Pallas next to the other asteroids that we visited with spacecraft. And so what you're seeing here is you're seeing that big round thing in the middle, and that's actually Ceres. This is all roughly to scale. So you've got Ceres right here in the middle. You've got Vesta up in the upper left corner, and these are all images from Hubble Space Telescope. Down in the lower left corner, that's Pallas, which is actually the second largest asteroid, a little bit larger than Vesta, but not nearly as dense. So we've got kind of an interesting asteroid family picture. But when we talk about these things as possible planetary objects, we're talking about how different they are actually from what we generally consider to be asteroids. So if you picture yourself in like Star Wars land, and you're zooming through your asteroid field, you've got chunks of rock flying everywhere, and you're picturing the things that are over here on the right of that image. And so those are the asteroids that we visited so far. We've got Eros and Itokawa, Ida and Little Tiny Dactyl actually. So these are spacecraft images of other asteroids, and you're noticing that they're much, much smaller, especially than Ceres. The story with Ceres goes like this. It was actually the first asteroid detected in the asteroid belt, but it was originally called a planet. They had gone looking for the missing planet between Mars and Jupiter, and they looked exactly where they should have looked, and they found Ceres. And so Ceres was initially thought of as a planet, and as you look at that surface, it seems to be reminiscent of a planet to me. I'm one of those planet people. I think round means a planet. And so Ceres is a really interesting story to tell, because it turns out that for a body that size, it's got a very low density. So whereas Vesta has a density of like 3,400 or 3,500 kilograms per meter cubed, which is basically the density of like a heavy rock, and a rock with a little bit of iron in it. Ceres actually, despite being so large, only has a density of 2,000 kilograms per meter cubed. And so when you think about materials that might be making Ceres up, it tells you that something low density must be involved in its formation. And in Ceres, we think that actually may be water. And so that round shape on Ceres, we think, is actually indicative of a subsurface ice shell. So if you think of the moons of Jupiter and the moons of Saturn, these round ice balls that are either differentiated or partially differentiated, they've got maybe an ocean down deep and then a rocky core. We think Ceres might be very much like that, but just with a rind of dust on the outside that's kind of protecting that ice from sublimating over the course of the solar system. So when we get to Ceres, it's going to be really exciting to see if we're right about that idea, if indeed Ceres is made of a bunch of ice, because it tells us something totally new and different. It would be the first confirmation, really, of an icy body interior to the orbit of Jupiter. We see that ice is common all over the solar system, but what might Ceres' surface look like? It might be very much like Callisto or like Europa, but just covered with a bit of dust on the outside. So I'm kind of excited to go and see what actually Ceres might be like, just to see that we've got this other type of object out there. So this is what we think. I don't know if it's too stretched to really be able to see, but this is what we think the interior Ceres might look like, where you've got an ice layer covered with dust, and you've got a silicate interior. So those are just one of the questions that we're going to try to answer when we get there. We can't see any impact craters so far on Ceres. We saw them on Vesta, we can see them on Pallas, we can see them on other asteroids, but we can't see any, even with better resolution, on Ceres than on any other on any other asteroid, at least remotely. And so why might that be true? Well, we think that that ice mantle maybe have had a chance to flow out and erase some of that. So there's a totally different idea. Another idea is that Ceres might actually be a body that has yet that is mostly filled with pores that might have not melted at all and just be kind of a ball of relatively low density silicates. So one of the exciting things that Dawn's going to do is use gravity, use GRAND, use surface spectroscopy and imaging to be able to tell the morphology of what's probably a unique body in the whole solar system. So I'm really excited to see that. So we'll actually just barely edge out new horizons in getting to, and being the first to get to an official dwarf planet, whether or not you believe that Ceres is a planet or a dwarf planet. It's still going to be a pretty amazing place. So I'm certainly looking forward to that. So just to wrap up, I'd like to invite everyone to participate in the Dawn mission. Go on to dawn.jpl.nasa.gov for more information about the spacecraft, the people doing the work, the science results. But also please join us in our efforts to understand the surface age of Vesta and mapping its features through participation in the Asteroid Mappers program. You can go to cosmoquest.org/mappers/Vesta, and that's going to be your chance to really participate in the ongoing science understanding Vesta. So let's wrap it up with maybe one or two questions. Let's see. We had a pretty good question, actually. So we had a question for the panel that was, let's see, where okay, so we posed this a little bit earlier, but I wanted to go back to this question of Vesta. So let's just go through the scientists and engineers that are left online, and why don't you give me your rundown? What do you think of Vesta as a planet, asteroid, both, something new, something different? Why don't you take it away, Chuck?
Well, Vesta looks like a dwarf planet to me. So
all right, how about you?
One vote for dwarf planet.
You vote for a dwarf planet. All right, yeah. Deborah, let's continue to poll the audience. What do you think?
Okay, well, it's not a dwarf planet by the AAU's definition, but it's a dwarf planet to me. I think the fact that it's got a differentiated interior means it should qualify as a planet.
How about you, Lucille?
To me, it looks like a small planet. If you compare to the other asteroids, which are really irregular in shape, of course, you see Vesta as a small planet.
All right, we got some planets. How about you, Tim? What's your perspective?
What's in a name, really? I don't think the name matters as much as interesting as it is, but it does look an awful lot like a planet, like others have said, with a differentiated core and that sort of thing.
And how about you, Vishnu?
Oh God, okay. I gotta watch my mouth. Yeah, I mean, I think I agree with Tim. I'm just gonna go with that. Yeah, it doesn't matter
agree,
what
actually.
Yeah, it doesn't matter what we call it. I think Vesta didn't care what we called it before we got there or before we found it. So I don't think it should matter now. So.
And it seems we just lost our host, Brittany.
Oh.
Oh no.
We're on our own.
I can tell you that we had a couple of comments from the audience also saying, Jose Rosado said, definitely Ceres, Pallas, and Vesta should be a class apart from the rest of the asteroids. So it sounds like the audience is in agreement with you guys that it is something special. We had a couple more questions I wanted to throw in Brittany's absence. We have, would Dawn be able to determine if liquid water exists below the surface of Ceres?
Sammy might have been able to answer that, but
Okay.
I don't see him on anymore.
No, I think
Of the tools we have, I mean, Lucille and Vishnu, would you agree that's probably, I mean, Grand would be able to determine water on the surface, but not subsurface. So
Yeah, I think gravity should be able to tell if there is subsurface ocean or something like that.
Okay. One kind of important question. When does Dawn arrive at Ceres?
Okay, the engineers.
I'll take that one.
Yeah.
We're currently scheduled to arrive in early 2015. A lot of that depends on how often we fire the ion engine and the planning between now and Ceres. So it's pretty variable, but it will be early 2015.
Okay. We were just talking about when we're going to arrive at Ceres.
Yep. 2015. Looking forward to it. I'm glad I get to experience the whole kickoff right there. So anyway, so with no further ado, thanks so much to the panel. Thanks you guys who are out there for spending a bit of your time with us. And this will be kept up on the YouTube channel. So if you want to send your friends to it, you can continue to comment. We'll try to track and answer more questions as those come up. And thanks so much for participating. Look forward to working with all of you in the future. So
and please do check out Asteroid Mappers. I'm going to put that up once more up on CosmoQuest. So that just launched today. We've got tons of images for you to look at, map surface features. If you've already been addicted to moon mappers, you will be even more addicted to asteroid mappers. I tried not to go through all of them last night, but it's pretty cool. So please do check it out and help these guys do the science that we need your help.
All right, well, let's sign off, and thank you all very much.
Thanks, everyone.